Okay, so note 6.7, so definite integrals. So it says an antiderivative of the function f of x is a function capital F of x whose derivative is f of x. All that means is if we have the derivative of capital F of x, that's the same as saying f of x. Okay? Remember, the antiderivative and the derivative are opposites. So when we look at the derivative and we think of an integral, they're the opposites of each other. So it says, let f of x equal 3x squared, and then the derivative equals 6x. The expression 3x squared is the antiderivative of 6x. And it says why? Well, if we think backwards, okay, and that is what the antiderivative is, we're able to say, okay, if our derivative is 6x, okay, what would our original function be? Okay, we're going to talk a little bit on what that means more in the next notes. Or, sorry, later on in these notes. So let's see. The first thing it wants us to recall is the power rule for finding a derivative. So remember, when we were finding the derivative, we were bringing down that exponent to the front, okay, and then subtracting 1 from the exponent. So for example, this would have been n x to the n minus 1. Okay, if we bring it in terms of an example, let's say x to the 5th, we know that the derivative looks like 5x to the 4, right? We bring down the exponent, subtract 1. Well, for the antiderivative, we're going to do the complete opposite. And our first step is going to be adding 1 to the exponent. Okay, so if we have x to the n, the antiderivative means we have x to the n plus 1. Our next step is to divide by our new exponent. So in this case, our new exponent is n plus 1, so I'm going to divide by n plus 1. Okay. The only thing different is when we take the antiderivative, we have to assume that some constant may have been there. So we write plus c. So again, this stands for a constant. Okay. That's because if you take the derivative of a constant, what happens? It goes to 0, right? So if we're looking at the antiderivative, we don't know if there was a constant number there. We don't know if it was plus 1, plus 2, minus 1,000. So we just say plus c to make note that a constant could have been part of the original function. Okay. So if I was to look at x to the 5th using that same example as the derivative, the antiderivative, our first step would be add 1 to the exponent. So this becomes x to the 6, and then we divide by that new exponent, which is 6, and then we plus c. Okay, so the antiderivative of x to the 5th is x to the 6 divided by 6 plus c. Because if I was to take the derivative of this, I would get x to the 5th. Okay, because they're the opposite of each other. Okay, so looking at another example here, what would be the antiderivative? Good. X cubed over 3 plus c. Okay, x cubed because we added 1 to the exponent. And when we added 1, we got a 3, so we're going to divide by that 3. And we always add c because we don't know if there was a constant there to begin with. Okay. For number 2, before we find the antiderivative, I'm going to make sure that I have everything in terms of exponents. So for example, that x cubed that's on the denominator, I'm going to move it up to the numerator. So I have my function f of x is equal to 5x cubed plus 6x to the negative 3 power minus 1. Okay. And then I'm going to find the antiderivative. So looking at just the first term, what would that be? 5x to the fourth, right? Because I add 1 to the exponent, and then what do I divide it by? 4, whatever that new exponent is. Okay, so the antiderivative of 5x cubed is 5x to the fourth over 4. Okay, what about for the next term?
6x to the -2 over -2.
Correct. So 6x to the -2, because if I add 1 to -3, it's now a -2, and then divide by that new exponent is -2. So this next part is where it becomes a little tricky, because can we add an exponent to -1? Can we add a number to our exponent? I mean, technically we could, right? But that's only going to be changing that number. What we actually have here is x to the 0 power. Correct? Because what is anything to the 0 power? 1. So I want you to think of this almost as your invisible 1. Okay? The reason why I write this now is because if I'm taking the antiderivative, I have to add 1 to the exponent, which means instead of x to the 0, I now have x to the 1, which is just what? X. And I'm going to write it out just so you can see it. So minus 1x to the first over 1. Right? If we're following the same trend, so you can see where everything came from. However, do we need the 1 in front of the x, or the 1 for the exponent, or the 1 for dividing? No. So if I was to simplify this, this would be 5/4 x to the fourth. Okay. It's nice if you can separate that fraction from your variable. Okay. Because remember, when we were talking about properties of integrals, we can take out a constant value. So we're just getting the habit of separating them from the variables. And then we have minus 3x to the -2, which of course we could bring that down to the denominator if we wanted to. And then we have minus x. Okay. So that would be our answer. Yes, thank you. Plus c. We can't forget plus c. Yes, we always include that plus c at the end. Okay. So number 3, we're going to do the same thing, but first I'm going to make sure that my function is in terms of all exponents. So instead of square root of x, I'm going to write x to the 1/2, and then same with this next one, plus 3x to the -1/2. Okay, so I'm going to take the antiderivative of this. Okay, and what do I get for the first term? So I'm going to be adding 1, good, so 3 over 2, so x to the 3/2, because I add 1, that's the same as adding 2 over 2. And then I'm going to divide this by 3/2. Remember, whatever our new exponent is, that's what I'm dividing it by. We'll simplify it later, because I know it doesn't look right to divide by the fraction like this. Okay, so then next I have plus 3x to the 1/2, because if I add 1 to that -1/2, I'm left with a positive 1/2. Divide by 1/2. Okay. Plus c. So I'm just going to rewrite this to make it look nicer. If I divide by a fraction, that's the same as multiplying by its reciprocal. So this is 2/3 x to the 3/2. Okay. Plus, how would this one simplify? 6x to the 1/2 plus c. That is our antiderivative. Okay, again, because when we divided by the 1/2, that's the same as multiplying by the reciprocal, so it would be 3 times 2, and that's how we got 6. Of course, you can also rewrite this and put it in terms of radicals if you wanted to. Okay, any questions on 1, 2, or 3? Okay, now let's look at some trig functions. Okay, so if we're given the integral of sine x dx, we know that that is equal to negative cosine x plus c. Okay, how do we know that? Well, what is the derivative of negative cosine x? Sine x. It gives us what is originally in our integral. Okay, so this is where I was talking about previously, where you have to be able to think backwards. Okay, so what if I took the derivative would give me this? So knowing that, what would be the integral of cosine x dx? Sine x plus c. Because what's the derivative of sine? Cosine. It gives this back here because they're opposites. Okay, then it brings us to the fundamental theorem of calculus. Remember, this was part 2 of the theorem that we wrote already on a previous note. So you've already seen this theorem before. It says if f is continuous on the interval a to b, so the closed interval, then the area under the curve of f from a to b can be represented by the integral from a to b, f of x dx is equal to capital F of b minus capital F of a. So f of b minus f of a, where capital F of x is the antiderivative of f. Okay. So for these ones, not only are we going to find the antiderivative, we're also going to solve it based off of the bounds given in the integral. So first, just starting off with this part here. So 4 minus 6x. We have to find the antiderivative. Remember that next to this 4, since it's a constant, is technically a what? X to the 0 power, right? Technically, that's 4x to the 0 power minus 6x. So if I was taking the antiderivative, what would 4x to the 0 power turn into? Good, 4x, and then divided by 1. But do I need to write that? No. Okay, what about the next term? Good, so I could, if I add 1, this is negative 6x squared over 2, and I can simplify that to be minus 3x squared. Once I find my antiderivative, I'm going to draw a vertical line, and this stands for solved at. So I'm going to take the antiderivative solved at negative 2 to 5. Okay. So following the fundamental theorem of calculus, I always start with capital F of b, which means I'm starting with the upper bound. So I'm going to plug in 5 into my antiderivative. So I have 4 times 5 minus 3 times 5 squared, and I'm going to put these in brackets because part of my equation is subtracting the 2. Okay, and then I'm going to plug in my lower bound, negative 2. So I have 4 times negative 2 minus 3 times negative 2 squared. Again, this is my f of b minus f of a. And then I just simplify. So from here, let's say this is an FRQ, this would be your answer. I would not simplify it, right, if you don't have access to a calculator. Okay. However, if it's multiple choice and you're forced to simplify, just make sure that we know our algebra skills and we're going step by step so we don't make a mistake. So here, 4 times 5 is 20. So I have 20. And then 5 squared is 25. 25 times negative 3, negative 75. Then bring down that minus. Then I have 4 times negative 2, which is negative 8. Negative 2 squared is 4. 4 times negative 3, negative 12. Okay, so technically I have negative 55 minus a negative 20, which gives me negative 55 plus 20, which is negative 35. And that would be my answer. Okay, so the area under that curve from negative 2 to 5 is negative 35. Yes?
So we do not include the plus c in like the first part where we saw the antiderivative?
So technically, yes, technically it's there. Technically this is plus c. However, since we have a definite integral, which means we have a lower and upper bound, that c goes away because we're not given any other information to solve for c, so we're just solving with the assumption that c is 0. Later, they will give us problems, for example, on number 7 when we get there, where we have to actually find c and solve. They give us more information. Okay. Any other questions on 4? Okay, number 5. The first thing I would do before I find the antiderivative is I would change this to be x to the 1/2. And I would also change this to be x to the negative 2. Okay. Make it easier when I take the antiderivative. Okay. So knowing that, the antiderivative of x to the 1/2 is going to be x to the 3/2 divided by 3/2, okay, minus x to the negative 1 divided by negative 1. Okay. I can simplify that to say this is 2/3 times x to the 3/2 plus 1 over x. Okay, and this is solved at 1 to 4. Okay, so from here, what number am I going to plug in first? 4, always the upper bound. So I have 2/3 times 4 to the 3/2 plus 1 over 4. Okay, minus, and then I'm going to plug in 1. So 2/3 times 1 to the 3/2 plus 1 over 1. Okay, again, FRQ, you would leave it as is. Okay, if not, you'd have to do some algebra here. And since we're going to be going on to the next notes, I'm just going to give you the answer. It should be 47 over 12. What I would do on your own time is solve the algebra and see if you can get to the same fraction. Okay, so that's going to involve, if you remember how these are written as radicals. Remember, something to the 3/2 power is, in this instance, 4 cubed, and then you take the square root of that number. Okay, this would be 1 cubed, and then you take the square root of that number. Okay. Okay, number 6, we have the integral from 0 to pi halves of 4 sine x dx. So the antiderivative of sine we know is negative cosine, right? So this becomes negative 4 cosine x. The number just comes down with it because technically we could have took this 4 and put it outside of the integral. Okay, so negative 4 cosine x. Then we have this solved at 0 to pi halves. So we have negative 4 cosine of pi halves minus negative 4 cosine of 0. Okay. Cosine of pi halves is 0, so negative 4 times 0. And cosine of 0 is 1. Okay, so we have negative 4 times 0, which is 0. Negative 4 times 1, which is negative 4, but minus a negative makes this a positive, so our answer is 4. Okay. Any questions 4 through 6? So again, since we're given a definite integral, which means we have a lower and upper bound, we do not need to worry about that plus c constant. Okay. Unless, on problems like number 7, we are given more information. Okay, so for example here's number 7, we're given the problem and then we're given the graph of the derivative. The problem says if the derivative of f of x is equal to x squared minus 2, and f of 1 is equal to negative 2, find f of 3. So our first step here would be to find the antiderivative. Okay. So the antiderivative of x squared would be x cubed over 3, good, and the antiderivative of negative 2 would be negative 2x and then plus c. From here, once I found that original function, I am given the information that f of 1 equals negative 2. So I can write negative 2 is equal to 1 cubed over 3 minus 2 times 1 plus c. And I can solve for c and actually replace that into my original function. So that's negative 2 is equal to 1/3 minus 2 plus c. I could add the 2 to the other side, and what would happen with those 2's? Cancel. And then I'm left with 0 is equal to 1/3 plus c, and what would be my last step to solve for c? Good, so c is equal to negative 1/3. Okay, which means I have the function f of x is equal to 1/3 x cubed minus 2x minus 1/3. Okay, that would be my original function if it asks me to stop here. But since it wants me to find f of 3, I need to plug in 3 for x. Okay, so 3 cubed is 27. 27 divided by 3 is 9. Negative 2 times 3 is negative 6, and then minus 1/3. Okay, I could turn all these into fractions with 3 as the common denominator and get 8/3. So for this type of question, since it's asking for what f of 3 is, I was able to give it the corresponding y value of 8/3. Yes. How did I get f of x? From this part here?
No, the one that says 1/3 x.
It's from up here.
Yeah.
Yeah, I just moved the 1/3 out. That's it.